The concepts we are discussing in this segment of sampling distribution of the mean are going to build the foundation to begin our discussion of statistical testing. The sampling distribution of the mean is defined as the probability distribution of means for all possible random samples of a given size from some population. Imagine that you have a population of 100 people and you can take all possible samples of a certain size, say a sample size of 5. You can then find the mean of each of these possible samples of 5. All of these means of all the possible samples will represent the sampling distribution. So our question would be, how much do sample means vary around the population mean? Keep in mind that although the sample mean is important, we are more interested in how likely it represents the population mean. Remembering that random samples rarely represent the population exactly. Using the concept of the sampling distribution will allow us to determine the chance the sample mean that we have observed from our chosen sample is either a common or a rare occurrence, given the variability of the possible sample means. For example, if we were to take a survey of 20 randomly chosen people at CSUN, collect information on their height, and then use that information to find the average height of 72 inches for our sample, the sampling distribution can help to tell us if this is a common occurrence. We have to think about the distribution of means for all possible samples of 20 people from this population and how common our mean is compared to that. The concept of a sampling distribution can be a bit confusing, so let's go through an example of creating a sampling distribution to hopefully make things more clear. Let's take an example of a population consisting of 4 people with BMIs of 22, 24, 26, and 28. If we were interested in a sample of 2 people, we can create a list of all possible random samples of 2 people from our total population of the 4 people. Let's assume for this example that we can choose data from the same person more than once, and it represents a different sample if they were chosen first versus second. All possible samples of the 2 people's BMIs would look like our table below, with 16 total possible samples. For example, our first sample has 22 twice. Our second sample consists of the observation of 22 and the observation of 24. Now that we found all of our possible samples, let's recall that the sampling distribution relies on the means of all possible samples. So we have to find the mean of all possible samples that we found. In this case, there are 16 total possible samples that we found. So we would have to find the mean of each. For example, to find the mean of our first sample, we would add the 2 observations, divide by the total number of observations, in this case 2, to find our sample mean of this sample of 22. We would continue this process with the rest of our samples to find each of the sample means of all of our possible samples of 2 from this population. We can then construct a frequency and relative frequency or probability distribution incorporating each of the sample means that we found and the frequencies of each of the sample means to create our sampling distribution of means as below. Our frequency distribution represents that we had 1 sample mean of 22, 2 of 23, 3 of 24, and so on, with the corresponding relative frequencies also listed. We can also construct a histogram of the relative frequency distribution of sample means to give us a visual of the sampling distribution of the mean. A mean of 22 would be considered more rare based on our sampling distribution since we only observed 1 mean of 22, versus a mean of 25, which would be considered more common based on our sampling distribution, as we observe several means of 25. There are 2 more symbols that we're going to discuss that relate to the sampling distribution of the mean. The first is the mean of all the sample means, also known as the mean of the sampling distribution. The mean of all sample means is symbolized as mu sub x bar, indicating that it is the mean of means. A property of the mean of all sample means is that it always equals the mean of the population, or mu sub x bar equals mu. Let's take the example we used before. The mean BMI from our population of 4 people is equal to 25, and the mean of all possible sample means taken from this population is also 25. This is not a coincidence. The next symbol that you'll commonly see related to the sampling distribution is the symbol for standard error. The standard error represents the standard deviation of the sampling distribution of the mean and is symbolized by sigma sub x bar because it is a standard deviation of means. The standard error equals the standard deviation of the population divided by the square root of the sample size, or lowercase n. So what does the standard error tell us? The standard error measures the variability in the sampling distribution and provides us with an indication of how much sample means deviate from the mean of the sampling distribution, which, remember, also equals the population mean. The standard error gives us a rough measure of the average amount the sample means deviate from the sampling distribution mean. Because the formula for the standard error relies on sample size, increasing the sample size, or n, will result in a smaller standard error, because remember, n was on the bottom of the equation for standard error. This means that increasing the sample size will result in less variability. This property will allow us to make more precise generalizations from samples to populations when the sample size is larger, which is one of the reasons why a larger sample size can be desirable for many of the statistical tests that we are going to talk about. The last concept I want to mention in this segment is the central limit theorem. The central limit theorem states that regardless of the shape of a population, the shape of the sampling distribution of the mean approximates a normal curve if the sample size is sufficiently large. Now note a couple caveats to that statement. The central limit theorem applies to the shape of the sampling distribution and not the shape of the underlying population, which might have any shape. The central limit theorem applies no matter what the original population distribution looks like, although the further from normal the population distribution shape is, the larger the sample will have to be to meet the criteria of being sufficiently large. Depending on the underlying shape of the distribution, a sample size of 25 to 100 might be considered sufficiently large. The central limit theorem works in part because the calculation of the mean of a sample tends to dilute the effect of any extreme observations.